Welcome to another topic in chemistry. Go ahead and start setting up your focus note pages. You can see that the topic is kinetic theory and specific heat. Fill in the date that you're taking these notes. And then the essential questions we will answer during this video lecture are: how does the kinetic molecular theory describe solids, liquids, and gases? So a little bit more of detail on states of matter. And then we're going to get into one specific measurement related to states of matter called specific heat capacity. So how do I use specific heat capacity to calculate the relationship between temperature, energy, and mass? That is our focus for today. Go ahead and pause the video if you need more time setting up those notes. Otherwise, let's get into it. So first of all, the kinetic molecular theory, this is what it states. All matter is made of particles, and those particles are always moving. Now, you know enough chemistry to know that those particles could be atoms or ions or compounds, formula units, molecules. Like there's different ways we describe particles in chemistry, but in general, whether you have a pure atom or a salad or a mixture of cleaning solution, whatever that matter is, there's particles inside there, and those particles are always moving. To think about what kinds of particles we might have and how they might look, what I want you to do is I want you to do a little thinking. So you're going to pause the video in just a moment, and you're going to imagine that you could look inside a sample of steel, a sample of apple juice, and a sample of the gas helium. So imagine this was a box, and this was like a microscope box, and this would be what you could see inside a sample of each of these. And then you're going to draw particles in those boxes. How would they be arranged? And maybe like a description of the motion. Because remember, that's what kinetic molecular theory is all about: particles and motion. So in like 2 or 3 words, add to your like underneath the box or whatever, but draw particles. What could you see if you could look inside the sample, if you could look at the particle level? So it's a particle microscope. And then in 2 or 3 words, what would the motion of those particles be like? So pause the video and do that kind of thinking ahead to sort of see where you're at in terms of understanding kinetic molecular theory and states of matter. Pause the video. All right, so now that you have thought ahead of what do you think these particles might look like, because we're going to call steel solid, we're going to call apple juice liquid, and we're going to call helium gas. So I want to break down some details about this. So you might already have all the notes you need, or just add to the picture kind of description that you already have. Let's talk about solids first. So here's what I would have drawn sort of as a particle drawing. So if I could see inside the particles of a solid, this is generally what they would look like. The particles are vibrating in place. There would be my motion description. So kinetic theory, the particles would be kind of evenly arranged, and they would be vibrating in place. They are highly attracted to each other. This is why the particles stay in kind of their own arrangement. Even if you bump into it or you drop it, unless you break the attractions because of, like a piece of glass, for example, when you drop it, that force is enough to separate the attractions, but then the particles that are still in the sample, they're still attracted to each other. But if I bump into like a desk or a wall, that force isn't enough to break apart those attractions. So in a solid sample, the particles are highly attracted to each other. They have their own shape and their own volume. So volume is how much space it takes up. So they have their own shape and volume. And if you add enough energy to these particles that are vibrating in place, so they're vibrating in place right now. If you add enough energy, you break the attraction, and the particles will turn into what is it? Yeah, a liquid. So then this is kind of the particle drawing I would have made for liquid. Notice that they're kind of clumped. There's some space, there's less space, more space, just kind of clumped together. Liquid. The particles are rolling over each other. So that's what we would say for a 2 to 3 word description: rolling over. So the particles are rolling over each other. They have mid-level attractions, not as highly attracted to generally the way solid particles are, but less attraction than solid particles, but more attraction than when we get to gases. So mid-level attractions. And these are generic terms for generally liquids. Some liquids are more attracted particles than others. Some gases more attracted than others. Some solids more attracted than others. So there is sort of a gradient of attraction, but in general, liquid particles will have mid-level attractions. This is why you can pour a liquid. If you tip over a liquid sample, the particles just have a continual stream because the particles are attracted to each other instead of just falling out in clumps. They have a definite volume, but not a definite shape. So, because the particles are rolling over each other, they'll kind of roll and fall over each other to match the shape of the container, but the volume is the same. So, if you have 1 cup of water in a cup measuring cup, and then you pour it into a bowl, it's still 1 cup. If you spilled it on the counter, it's still 1 cup. But the shape of all of those things, the cup, the bowl, the counter, all of it would be different shapes, but it's a definite volume. All right, think about what we did so far: kinetic molecular theory, particle drawings, liquids, solids definitions. Write a level 1 question so far. Pause the video, look at your guide on Schoology for sentence starters if you need it, but write a level 1 question. All right, come on back. So after I have my mid-level attractions, I've got my liquid. If I add enough energy, I will break those attractions and my liquid sample will turn into, yes, a gas. So here's what I would have drawn for a particle picture for gas. And then we would say that the particles move in random straight lines. So that would be my 2 to 3 words. So they move until they hit something, and then they move into another direction until they hit something. They can hit each other, they can hit a container, they can hit a wall, they can hit a person. So, like the atmospheric pressure that you feel around you, like if you wave your hands back and forth, which I'm doing right now, I know you can't see me, but if you wave your hands back and forth, you can feel the gas particles in the air around you colliding with your skin. So the gas particles move in a random straight line, high energy, until they collide with something, then they bounce off into a different direction. Those collisions are what cause pressure. So if you have gas inside a balloon, the reason that the balloon expands is because the particles are causing pressure when they collide with the side of the balloon. Same with the air in your tires or the atmospheric pressure around us. We feel that pressure differently if we're high in the sky or lower in a mountain valley, but that pressure of gas particles colliding, that's what causes pressure. All right. The shape and the volume are not defined. So your shape could be whatever container it's in, and the volume, because there's so much space between particles, I can condense or compress a gas sample the way I cannot a liquid or a solid. So it fills as much space as however much kinetic energy allows. And maybe you remember this from previous science classes. Kinetic energy is energy of motion. So because the particles are moving, they have kinetic energy. And if they have more kinetic energy, they will move more and fill up more space. That's sort of the idea of gas particles. As I mentioned, so here's a visual example. This is a piston of some kind. Could be a piston chamber in an engine or somewhere else. But here's my gas sample. Because there's so much space between the particles, I can force those particles to go closer and closer together, which maybe you can imagine is going to cause more pressure because there's more collisions because there's less space. And then the other thing is that in general, we kind of ignore the attractions from one gas particle to another gas particle. Because they're moving so fast compared to other particles, we really say they're not attracted to each other. Now, that is a little bit of an ideal situation, and we'll talk more about gases next week. But in general, this is how the kinetic molecular theory describes gases. All right, let's talk just a little bit more about kinetic energy. So, as I mentioned, kinetic energy is the energy due to motion. If you have more energy, then you'll have more motion, which means you have a higher temperature. So now I want to start connecting things like energy and temperature, and also we're going to talk about heat also. There is something related to kinetic energy and temperature called absolute zero. Maybe you've heard of this before. Absolute zero is in the Kelvin scale of chemistry versus Celsius versus Fahrenheit. So 0 Kelvin would be negative 273 degrees Celsius or negative 460 degrees Fahrenheit. So to give you an idea, right? So think of it this way. You have a lower temp, which means there is less motion, which means there's less energy. So it'd be all the opposite. So absolute zero is the moment where there's no kinetic energy. That's why it's zero, absolute zero. But if there's no kinetic energy, that means there's no motion, right? So all motion stops. So it's so cold that I'm not even vibrating or shrinking. That's what this, or shaking. That's what this cartoon is showing. So absolute zero is 0 Kelvin. And so we use Kelvin a lot in science, especially when we're talking about gas particles, because you won't have any negative numbers. Well, and why can't you have any negative numbers? Well, think about what happens at 0 Kelvin. Look at what happens there. Well, you can't go slower than no motion. So you're already stopped motion. And I will tell you that absolute zero is a theoretical number. We haven't reached it, but there is a lab in Switzerland that has gotten really, or maybe it's Netherlands. Anyway, it's really close, like within decimal places of 0 Kelvin. So it is a theoretical number, but it is something that people are working towards. All right. So that's the idea, just a connection, because this is something you might have heard before, but it's related to the kinetic theory and kinetic energy. So I bring it up to kind of think about. All right, go ahead and do a level 2 kind of question so far. Drawing another particle, so like pick a different, like any type of matter, any classification, a mixture, an element, a compound, and ask and sketch a particle picture of it. That would be a great level 2 kind of question. But come up with any of your own and come on back to the video when you're ready. All right. So the next thing I want to do is I want to kind of start relating kinetic particles and energy and states of matter to something called specific heat capacity. But before we do that, I want to talk about heat versus temperature. So temperature is a measure of kinetic energy. So it's measuring particle motion. And it would either be, in science, we either use Kelvin or degrees Celsius. We don't use Fahrenheit because these scales are based, this is an absolute scale, that's why there's no degree symbol. And this is nice because if you compare it to water, 0 degrees freeze, 100 degrees boil. So that's why we like Celsius. But it's a measure of kinetic energy. To convert between Celsius and Kelvin, it's a factor of 273. So right now it's about 22 degrees Celsius. That's usually about what room temperature is. So that would be about 295 Kelvin. So take your Celsius plus 273. That is your Kelvin temperature. Or the opposite. If you're given Kelvin, trying to get to Celsius, take the Kelvin minus 273. That gives you Celsius. We will go back and forth between Kelvin and Celsius quite a bit in science, so that's why I want you to have that conversion. But the good news is it's not super tricky. Okay, so temperature is only measuring kinetic energy. Heat is the total amount of energy available. That could be due to friction, due to kinetic energy. It could be due to thermal energy. There's lots of different ways that heat can produce energy, and it's measured in joules or calories or capital C calories, which is really like 1,000 calories, and that is what food. So food calories are capital C, lowercase calories. But the point is that these are words you've maybe heard of, all related to heat, not temperature. Just to give you a reference, 1 joule is about 0.239 calories. So there's a conversion that if you needed it for different problems or labs, there is our conversion. But we could use our DA skills to convert between calories and joules if needed. And again, capital C calories is just 1,000 regular calories. So then 1 joule would be like 239 big calories. Okay, so that gives you a little bit of reference of when we talk in science about heat versus temperature, both of them are related to energy, but temperature is only measuring kinetic energy and heat could be any kind of energy that is present. Okay, now that brings me into this thing called specific heat capacity, which is kind of a really cool way, and you can see lots of cool connections in your life related to this thing. Now, this little cartoon, I love the specific heat capacity of water, says the fish. That will make more sense in just a bit. So, the definition of specific heat capacity is the amount of heat 1 gram of a substance can absorb before changing its temperature 1 degree Celsius. So if you had 1 gram of water, how much energy could that 1 gram of water absorb before it would go from 22 degrees Celsius to 23 degrees Celsius? So that idea, so how much can a sample absorb until it changes its temperature? That's the idea. So the idea here with this fish is thinking, well, water has what we consider a pretty high specific heat capacity. That means it can absorb a lot of energy before it changes its temperature. So if it's really, really, really cold outside, like the air temperature, your water doesn't get super cold right away, or the opposite. If it's really hot outside, the water stays cool for longer. And that can be really good, obviously, for fish, but it also works really well for humans when it's really hot outside, but the water is cool to like for a recreation or cooling off, or the opposite. Think of like ice fishing people. Even if the temperature starts to warm up, that ice doesn't disappear immediately. So it's safe to be on it a little bit longer, even when it gets warmer in the late winter or early spring. So anyway, specific heat capacity is explained. So if you're holding on to something and it's getting really warm versus something you're holding on to and it's not getting very warm, that has to do with specific heat capacity. All right. The math formula for it is capital C equals Q over, this is a dividing line, M delta T. Okay, what does that mean? Capital C is the symbol for specific heat capacity. So to calculate specific heat capacity, you need to know Q divided by M times delta T. Q is your heat energy. So this would be joules or kilojoules, because remember, that's what heat is measured in. M is your mass. So how much of that sample do you have? What is its mass? And then delta T is change of temperature. So did it go from 5 degrees to 80 degrees, or did it go from 9 degrees down to -5? Whatever the change is, that's what goes in delta T. So here's another little cartoon. A wooden spoon gets kind of warm when you put it over heat. A metal spoon is way too hot. Well, you can see that their delta T, the change of temperature from the heat, would be the same. The mass would be maybe similar, but the amount of heat they absorb is very different because of the energy inside the sample. The particles inside the sample can absorb different amount of energy before they start vibrating more and creating more kinetic energy. So that idea behind, again, why does that happen when you're cooking with a metal spoon versus a wooden spoon? Why does one heat up differently? That is specific heat capacity. So connections to your life. All right, here's a couple more examples. So just giving actual numbers. So silver's specific heat capacity is 0.235 joules per gram degree Celsius. So if you have 1 gram of silver raising 1 degree Celsius, it has to absorb 0.235 joules. Okay. Aluminum can absorb 0.903 joules before 1 gram of aluminum would change its temperature 1 degree. So then look at what water's is, 4.184 joules for 1 gram of water to change its temperature 1 degree. So this is where you can see relative. We say that water is high because look at these two are both less than 1 and water is higher than 4. So water we say has generally a high specific heat capacity, meaning it can absorb a lot of energy before the sample changes temperature. That's specific heat capacity. All right, to make a connection about this, think about this question. On a sunny day, if you've ever been to a pool of some kind, either at someone's house or at a park or at a gym or something, if it's outside, on a sunny day here in Minnesota in summer, let's say July, why does the concrete around the pool get really, really hot, but the water is so much cooler? Maybe you've noticed that you're walking around safely on the concrete and your feet get really hot, and then you jump in the pool and the water is so much cooler. Why is that? Think about that for a moment. Pause the video. Think about that. All right, do you have an answer? It's specific heat capacity. So which one of them must have a lower specific heat capacity? Yeah, it must be concrete. Concrete absorbs, it takes less energy for the concrete to increase its temperature. So a lower specific heat capacity. So a lower amount of joules needs to be absorbed before its temperature starts increasing. So the energy coming from the sun, the concrete is absorbing it, the water is absorbing that same energy from the sun, but the lower specific heat capacity, those particles inside the concrete sample, they don't have to absorb very much energy before they start speeding up and getting warmer. That's the idea there. All right, go ahead and do a level 3 kind of question. Maybe you want to make up a different example like this. So instead of concrete and pool, come up with some other example from your life. That'd be an awesome level 3 question to try to explain with something to do with specific heat capacity. All right. All right, so that brings us to the end of our first day of this unit on kinetic theory and states of matter kind of stuff. So go back and finish any COSTA questions, write your summary that answers. We did have 2 separate EQs for today, so do a little summary for both of them. And then I do have a specific heat practice assignment. It's 4 problems just to practice plugging in the numbers, solving, canceling your units. It's really algebra more than, it's not DA, it's not stoic. So think of it really as like algebra for that C equals M over, or C equals Q over M delta T formula, specific heat practice. There are some unit practice problems. They're in the week 11 folder, the first 10 of them. That will help you process today's notes. I do have a kinetic molecular theory supplemental reading. It is optional, but it does fill in a whole bunch more details. So for those of you that like reading, it might be another way to kind of supplement what you learned about today and the rest of this unit. And then just old stuff reminder, Unit 5 quiz should be done, the Silver Lab Report. If you're watching these notes on the day they were assigned, this lab report is due on Friday. And that means the next time I see you, if you're watching these notes on the day it was assigned, the next time I see you is our last Zoom. So again, if you're watching this on either February 24th or February 25th, Monday, March 1st is our last Zoom, and you have all 5 classes. So just remember that. Talk to your individual teachers about specific questions. But that's only specific to Try to 2021. All right. Thank you so much for joining me with some more information on chemistry, specifically kinetic molecular theory and specific heat capacity. See you next time. Bye.